Hello everyone, welcome to 𝗓𝗂𝘂𝗀𝗃. So today we'll be talking about special shear wall. So all of you know that in our IS 456-2000 section 42 gives us the way to design plain concrete wall. So if you see, suppose we have a RCC wall and it is meant to take the, you can say, vertical loads or gravity loads, and also it will have the moments in it, right? So the vertical force and the moments, if we design the you can say RCC wall, suppose this is an RCC wall and it is designed as per IS 456-2000, okay, and most probably it is section 32 as I remember. So if it is designed as per IS 456, for what are the, you can say, load, what are the, you can say, elements it will be there? So it will be vertical force, or I won't say, I will write there because I will be discussing this later. So if the RCC wall in your building is designed as per section 32 of IS 456, then that wall is, we mainly call it as plain concrete wall. So it is just a normal wall. It can be an infill wall also, okay. So it is just a concrete wall, and it is designed for the moments and the forces coming on it, vertical loads coming on it, okay, fine. Now Bureau of Indian Standard, BIS, Bureau of Indian Standard says, if this RCC wall, suppose we have this RCC wall, and if this RCC wall is meant to take the lateral forces, so suppose we have, let me draw here, suppose we have a frame like this, okay, frame like this, and this is also extended actually. Let me draw it like this, okay, in this direction also. So I'm drawing a frame kind of like this, Control Z, okay, fine. So just ignore this extra part. So if we have a frame like this and we are providing some RCC walls, suppose we are providing some RCC walls here and here also, suppose here and here, okay. So suppose we have provided some RCC walls along with our columns. So we have a column here, we have a column here, and maybe we are providing another RCC wall like this, and we have a column here and here, okay. So these are my columns and these are my walls, okay. So what are the loads we have? Obviously we will be having vertical loads on it. So the first we will write it as gravity loads. So obviously obviously whenever we are designing a RCC wall, even if it is designed as per IS 456, obviously it will be designed for the gravity loads also, right? So the gravity loads, it is applicable in this case also. So now with the gravity load, if you design these walls to take the lateral forces, that means suppose we have wind or seismic load, or you can say earthquake forces. Okay, suppose these are my columns. So if I just write that, suppose we have earthquake force EQ X from this direction and maybe EQ Y in this direction, from this direction, and you are saying that when these lateral forces are coming, these walls should take the lateral force. These walls are not only not only for infill, the purpose of infill wall, not only for the purpose of taking the gravity loads, but it should resist the lateral forces also. It should resist the lateral forces also. That means these walls are the lateral load resisting elements. Okay, so we have a frame. Okay, basically if we draw a column beam frame, so this is my column beam, and even if there is lateral force, so these columns will be taking those lateral forces, right? So these columns and the beams are the elements which are resisting the lateral forces. But here in this frame, we are designing these walls in such a way that these walls are also taking the lateral forces. These walls are also taking the lateral forces. So that means these walls are you can say part of our lateral load resisting system. Okay, including, suppose we are designing the columns also for taking the lateral forces, but so that means including the columns, these walls are also taking the lateral forces. So in that case, BIS says that when the RCC walls, okay, when the RCC walls are designed to take the lateral forces, or are meant to take the lateral forces, or as a part of your lateral load resisting system in your building, in that case those walls, let me write, if walls are part of lateral load resisting frame, or I can say lateral load resisting system of the building. Walls means RCC walls. Okay, RCC walls I'm taking. So lateral load resisting frame or lateral load resisting system of the building, in this case walls should be designed as per IS 13920 provisions. Okay, so whenever the RCC walls are meant to take the lateral forces or meant to resist the lateral forces, in that case those walls we cannot design with IS 456 only. It needs to be designed as per the clauses or as per the provisions of IS 13920. Here you can see. So in this case, those walls will be called as special shear wall. Those walls will be called as special shear wall. Okay, fine. So normally a shear wall or a plain concrete wall can be like this, and we can provide, you can say, reinforcement like this, We can provide reinforcement like this. And we can have the stirrup also. In the similar way, we can have the, Control Z. Similar way, I think I have drawn the wall very small. Let me draw the wall a bit bigger so that I can show you properly. So suppose this is my stirrup, and here I have my wall. Though I have made it very big, it won't be like this actually. So let me just drag it a bit. Okay, let us consider like this, and we'll be providing the reinforcement like this. Okay, we'll be providing the reinforcement like this. Fine. So it can be, so this is my thickness of the wall, TW, and this is the length of the wall, LW. Now this wall, if it is designed as per IS 456 provisions, just as a normal plain concrete wall, then it will be just a shear wall. We can call it as a shear wall, okay, because it will have some you can say stiffness to you can say provide resistance against the lateral forces. But though we are not designing it, or these walls are not designed for taking it, right? But when we are intentionally, or we want these walls to take the lateral forces, and we are designing it as per IS 13920 provisions, then we'll be calling it as special shear wall. Special shear wall. Now, when a special shear wall is designed, okay, when a special shear wall is designed, it is seen that, see, we have a wall like this. Initially it will take gravity loads, but when it is a special shear wall, then it is not only meant to take the gravity loads, but it also resists major amount of the lateral forces. So if the lateral force is coming like this, then the deformation of the wall will be like this. So if you see, as it is deforming like this, so this end zones, or this extreme fibers of the wall, here what we will have? Here we will have tension, and here we will have compression, right? So that means the fibers in this zone will be under high tension, and the fibers in this zone will be under high compression. So that means the strength requirement, okay, the strength requirement of the end fibers will be higher. Fine. So in that case, in the practical use of the, you can say, shear wall to resist the, you can say, lateral forces, it is very necessary to provide stiffer zones at the ends. Okay, so if I just draw another section, it is necessary to provide stiffer zones. Suppose this is my stirrup, and I don't know why it is doing like this. Let me draw it properly. For some reason it is not working properly. I don't know why. Let me draw with it with my mouse. Okay, with the mouse it is working properly. Fine. So let me just okay, fine. So now I have drawn another section of the shear wall, and now what I will do, I will take a length. I will tell you what will be the length. So I'll take a length at the ends. So these are my extreme ends. Okay, and I will provide closely spaced reinforcements here. Closely spaced reinforcement here, and also a separate ring, or you can say a separate stirrup, like a column, an individual column. Okay, and then we'll be providing reinforcement at the mid like this. Like this. So this is my thickness TW, fine, and this is my length LW. So what I did, it is the same shear wall, but as the strength requirement is higher at the end zones and it is less at the mid zone, so we have provided closely spaced reinforcements, or you can say column like reinforcements at the end zones, and we have provided a general uniform reinforcement at the mid zones. Okay, maybe we will have some ties also there, that is we will discuss later, the design criteria. So these end zones where we are providing reinforcement like a column, okay, like a column, this length of the end, it can be of 2 times the thickness of the, it can be at least 2 times the thickness of the wall, and this length should not be greater than 0.2 times LW. Here also it should not be greater than 0.2 times LW. So we can provide a stiffer zone at the 2 ends, okay, or you can say a column like reinforcement to make it more stiffer, the end fibers to make it more stiffer, and this length should you can say you can begin with 2 times the thickness, but it should not be more than 0.2 times LW. Fine, it should not be more than 0.2 times LW. Fine. So as the stresses are higher at the end zone, so we can provide some stiffer zones to take those stresses. So in that case, the design will be more economic, or the design will be more proper, you can say. Fine. So these stiffer zones, whenever the, you can say, the load is increasing, the number of stories are increasing, the stresses at these stiffer zones, or you can say the stresses at these end fibers will be increasing, and the requirement, okay, maybe the length or the strength requirement or the stiffness requirement, or whatever you say, the strength requirement of these end zones, I will say, will be higher, will be increasing. Okay, so these end zones which we have made stiffer of a shear wall are basically called, these are my end zones, right? I'll write EZ. So these end zones, we call it as boundary. Element. Okay, so this boundary element, it's not always compulsory. General practice in any kind of shear wall, it is a good practice to provide stiffer zones at the ends. Okay, but there is a criteria when it is compulsory. Suppose, obviously, here we will be having tension, here we will be having compression. So when when, all right, when the stress, or specifically compressive stress, at extreme fiber is greater than 0.2 FCK. FCK is the grade of concrete. So as per IS 13920, when the compressive stress at the extreme fibers, you can see these are my extreme fiber here, right, taking the compressive stress, and vice versa. If the force is coming in this direction, so this end will become my like this will be taking the compressive stress, this end. Okay, this end will become under compression and will be having compressive stress here. So when the extreme fibers are taking compressive stress, if that compressive stress you can say crosses 0.2 FCK, okay, 0.2 FCK, so in that case boundary element is mandatory. Otherwise, if it is less than that, then it is your choice. It is a good practice to provide you can say reinforcement distribution in the shear wall like this, or you can have a special shear wall like this. But when the stresses at the extreme fibers reaches 0. I can say crosses the limit of 0.2 FCK, in that case providing boundary element is mandatory. Now, how we will be providing the boundary element? What will be the dimension of the boundary element? So obviously the initial dimension of the boundary element, we can begin with, suppose this is my shear wall highlighted cross section. So initially we can begin with a boundary element of thickness TW, which is same as my shear wall, and length maybe 2 times TW. Okay, length maybe 2 times TW. Fine, so we can begin with this. Now if you see that you are increasing the you can say length of the boundary element, suppose first of all what we will do, the first thing we will keep this fixed, we will not increase it. So what we will do, we will increase this TW, I can say this length. First of all we will increase this, right? So if I just name it, suppose L1, so first we will say increase L1. So first of all we will start increasing the L1, right? And by increasing the L1, what we will see, whether the stress, we will check whether the compressive stress is less than 0.2 FCK, less than or equal to 0.2 FCK or not. Okay, fine. So if it is not less than 0.2 FCK, when the length reaches 0.2 LW, so we know that this distance from here to the furthest end, it is LW. So when this length reaches 0.2 LW and still the stress is not less than 0.2 FCK, or not equal to, at least not equal to 0.2 FCK, so in that case what you have to do, the next what we will do, the next we will increase TW. So then we will increase the TW. Okay, then we will start increasing the TW. Fine. So how will we be increasing the TW? How will we increase the TW? So in that case, you will have a shear wall like this. Suppose this is my boundary element, and here I have the wall like this. Okay, so basically suppose I will draw a section mark. Fine, so not section mark, it is a continuous wall. So in the other direction also you will be having boundary element. So here what we have done, now this is my thickness of boundary element and this is my thickness of wall. This is my length of boundary element, and from here to the other end of the boundary element, okay, it will be my LW. Fine, so here we will be providing reinforcement like this. Fine, we will be providing reinforcement like this, and here we will be providing the normal bound, you can say, as we provide the wall reinforcement as usual. Okay, maybe horizontal reinforcement also will be there, and in this case we may provide some links also. Okay, so when we are increasing the, you can say, dimension, both thickness and you can say the length, so as the area of the boundary element is increasing, so obviously the stress will be decreasing, because we know force by area equal to the stress. So the if area is increases, so the stress is inversely proportional to area. So if area increases, the stress will be decreasing, right? So it is basic simple physics. So obviously in that case, when the length, increasing the length is not working out, we have to increase the thickness. Okay, we need to increase the thickness. So increasing the thickness will be very effective. Okay, increase the thickness will be very effective. Now what we have done, we have provided, suppose that we do not have to you can say increase the thickness if increasing the length reduces the stress less than 0.2 FCK. Okay, so now suppose our stress is less than 0.2 FCK, but still to make it stiffer, we have provided some end zones, or first of all we had you can say the stress more than 0.2 FCK in some floors. So we have suppose multi-story building of G+10 or G+12, and up to 5th floor or 6th floor we had the stress as 0.2 FCK. So what we have done to reduce the stress, we have provided the boundary elements, stiffer sections. Now after 6th floor, if stress, what I meant compressive stress at the extreme fiber, okay, so that I am not writing again, the compressive stress at the extreme fiber, if it get reduces, or when it is less than or equal to 0.15 FCK, okay, when the stress in these end zones, compressive stress and these end the fibers are less than 0.15 FCK, in that case you can discontinue the boundary element. So what it meant to say, suppose you have, what I meant to say, that suppose we have shear wall and suppose we have 2 floors here. Okay, we have 2 floors here. Now here what we have done, up to this floor, suppose this is some 5th floor, so below also we have some floors. I've just drawn it like this. Okay, so suppose this is my 5th floor, this is my 6th floor, this is my 7th floor, and again so on we have some. Now up to your 6th floor, the stress here, compressive stress, was greater than 0.2 FCK. So then what we will be providing? We will be providing boundary elements here. So we provided boundary elements to take care this stress. Now after this floor in this end zones, suppose, or this end fibers, now the stress is compressive stress is less than 0.15 FCK. Okay, so what you can do after this floor, after the 6th floor, from 7th floor, or sorry, after the 5th floor up to 6th floor, we have provided the boundary element. Now beyond this we can discontinue the boundary element, so we do not have to provide. Suppose up to 6th floor we have provided like this. Okay, up to 6th floor, and after 6th floor then you can discontinue the boundary element and you can provide general uniform reinforcement like this. Okay, then this stiffer zone is not required. Okay, then this stiffer zone is not required. I hope you got it, that when you can discontinue the boundary element, when the stresses of the extreme fibers and the compressive stresses, remember compressive stresses, the extreme fibers get get reduced less than or equal to 0.15 FCK, then you can say discontinue the boundary element. But in general practice we do not discontinue the boundary element. What we do, we provide a column like arrangement here. But in this we do not design those ends as boundary elements, because we have to design the boundary elements also. It's not like that we just provide some reinforcement and it becomes boundary element. Not like that. We have to design those ends as boundary element. But when the stress is less than 0.15 FCK, we may provide a column like arrangement at the ends, but we do not have to design it separately as boundary elements. Okay, so we can calculate the general reinforcement in the whole shear wall, and then we can just provide you can say column like arrangement at the ends. And the length, now you can decide, which will be in between 2 times TW to 0.2 times LW. Fine. And one more thing you have to remember, that any end zone, any stiffer zone, any boundary element must have at least 4 bars of 12 dia. Okay, so whenever you are discontinuing the boundary element but you are providing some column like reinforcement, you have to make sure that this end zone is having at least 4 bars of 12 dia. Fine. But when you are designing the ends as boundary elements, when the stress is greater than or greater 0.02 FCK, in that case remember, at least 0.8% AST you have to provide it. 0.8% of, remember, 0.8% of gross area you have to provide AST when you are designing it as boundary element. When you have discontinued the boundary element but you are providing some wall like column like arrangement, in that case it is not compulsory. In that case you have to follow, just for the overall shear wall you have to follow the minimum reinforcement requirement that we will discuss later. Okay, for the whole shear also we have the you can say minimum reinforcement requirement. As per this you provide the distribution, and then you just provide a column like arrangement at the ends by providing some extra bars or providing some stirrups like this. Okay, but it should have at least 4 bars of 12 dia. Even when boundary element is not required but you are providing the a stiffer zone like this, okay, for a better performance of the shear wall, in that case also at least 4 bars of 12 dia must be there. 12 dia or more than that. Okay, not less than 12 dia. Fine. Because these boundary elements, we are considering it as a column only. Boundary elements, actually, boundary elements, we basically design these end zones as short columns. So you all know that as per IS 456, we have this criteria that the columns should have minimum reinforcement dia of 12 dia reinforcement, and it should be at least 4 number of 12 dia bars. So the same is applicable here. When you are providing the boundary element, it is like a column and it should have at least 4 bars of 12 dia. Okay, it should have at least 4 bars of 12 dia. I hope it is clear. Okay, I hope it is clear. Now there can be, see, when this length of the boundary element, it can reduce. Suppose, now what you can do, suppose we have, let me discuss from here only. Suppose we have this multi-story building and we have this kind of floors, and at every floor we are having the boundary, you can say shear walls and boundary elements. But in that case, what you can do, up to a certain floor, maybe the strength requirement is higher. After that, maybe the strength requirement gets reduced. So what we do in case of columns, we do, suppose we have floors like this. So up to a certain floor, the column dimension is like this. Then we may reduce it with maintaining a proper slope. So we may reduce it, and here we may reduce it like this at one edge, or maybe from the center also you can reduce. Okay, I'm showing it from one edge. What we have done, we have reduced the column dimension. Okay, as per the moment capacity, because the requirement of moment capacity. Same for the shear wall. When we have, suppose, shear wall with boundary elements or shear wall without boundary elements, maybe at certain floor the shear wall thickness will be TW1. At this next floor, not at immediate next floor, actually, maybe after every 4 floors or 5 floors. So maybe obviously the strength requirement or the moment capacity requirement will be reduced. Then what we will do, then we will reduce the thickness of the shear wall, maintaining the slope for the bar. Okay, maintaining the slope for the bar, you have to keep this in mind. So you just have a look on the IS 456, there minimum slope or maximum slope is defined. Okay, not minimum slope, maximum slope is defined, or you can refer ISP 34 also. So based on that, what should be the slope, based on that we can reduce the thickness. Okay, not only based on the slope of the bar, but based on the, first of all, based on the you can say moment capacity requirement. Then you have to check that the thickness we have provided for this, the slope that we will be providing for the bar, whether it is meeting the requirement of the SP34 or the codal provisions or not. If it is not, then you may have to provide the thickness even if it is not required more than that. Okay, so then again the next floor we may reduce the shear wall dimension here. Okay, and if we have boundary element, then again the same thing will happen. Like column, the boundary element dimension also get reduced. So when the boundary elements are there with shear wall, so you can see the overall length may reduce from after certain floors. The overall length of the walls may reduce after certain floors. Right, after certain floors, overall, see, because I am reducing the boundary element length and the thickness of the wall also. Okay, so thickness is okay, but whenever I am reducing the boundary element dimension, so it will lead to reduction in the overall length of the shear wall. So that also we need to keep it in mind while designing. Fine. One more thing we can do, that we can provide uniform thickness or uniform you can say boundary element size up to maybe 10 floor or 20 floor. Instead of reducing it at every 5 floor or 6 floor, we can have a throughout same thickness. But what we can do in that case, we can reduce the grade of concrete, because if you see, the stress limit is related to the stress limit is related to the grade of concrete. Also this one is related to the grade of concrete, right? So here we may suppose up to fifth floor. Suppose I have a 20-story building, and after you can say 12th floor, after 12th floor, the stress reduces. The stress, you can say, reduces less than 0.2 FCK. So maybe up to 12th floor we have provided M30 grade of concrete for the shear wall, and maybe where the stress requirement or the induced stress is less, so we can see that this, even if you provide M25 grade, then also if we calculate 0.2 FCK, the stress will be less than this, less than 0.2 FCK. Then we can reduce the material grade also, grade of concrete, grade of steel. Generally grade of steel would not change, but the grade of concrete we can vary from floor to floor. From a certain, after a certain height, we can reduce the grade of concrete. We can reduce the thickness also with this. So both you can work out whether you can keep one constant, another you can vary, or you can vary both thickness and grade of concrete. So that will optimize your design. What it will do, it will optimize your design, right? So that means all these things, all these you can say boundary element, you can say moment capacity requirement for the lateral load resistance, so the stresses more than and less than limit, okay, the length of the boundary element, the design of boundary element, design of wall. So all these things are, you can say, mentioned, written clearly in our code IS 13920. The minimum reinforcement criteria for the boundary element, the minimum reinforcement criteria for the you can say shear wall, or you can say this wave part, we call it as wave. So this wave part, or as the shear wall as a whole, this is also defined. Okay, so a special shear wall, basically our topic was introduction to special shear wall. So a special shear wall is nothing but a RCC you can say reinforced concrete wall, which is meant to take the lateral forces mainly and designed as per the IS 13920. This definition is as per the BIS. Okay, so those are my special shear walls. And those concrete walls which are designed as per IS 456 and not actually designed for taking the lateral forces mainly, major lateral forces, those we can call it as plain concrete wall. Like a concrete wall can be, like if you say that I want to design my infill walls, that means my partition walls as concrete walls, like we do in the Maivan construction. If you see, when the Maivan formwork technology is introduced in some high-rise structures, so in that case there is shear walls, there is your partition walls, but both shear wall and partition wall, the column, beams and slabs are casted together with concrete. So do you think all the walls present in the you can say building will be the shear walls? No. Basically the partition walls are designed as a plain concrete wall as per IS 456, and wherever we have, you can say, introduced the shear walls, those shear also concrete wall casted together, but the detailing, the design, okay, the rebar that we'll be providing after the design, everything will be different. Those walls will be designed as per IS 13920. So many people have this question also, that what we should do when we design you can say Maivan structure, Maivan wall structure. So remember, Maivan wall structure is not a structure, not a structural system. Maivan wall is not a structural system. Maivan is just a formwork, okay, aluminium formwork, okay, which you can say where you can, like, it is not as the general formwork, right? So what we do in case of Maivan construction, we cast the whole floor together, including the slab, beam, column, walls, whatever it is. And in the Maivan construction, it is often, like, it is not compulsory that you have to make your you can say infill walls, or you can say your partition walls as concrete itself only. Okay, but in high-rise structures, what they do, it is seen that it is a general practice that those walls are also made as my concrete walls. Okay, the partition walls are made as concrete walls. So in that case, the shear walls and the concrete walls, plain concrete walls, are casted together, and most of the time people get confused that those walls are also will be acting as shear walls or not. Okay, or those walls also will be designed as shear walls or not. No, exactly, the partitions will be designed as partition walls only, as plain concrete wall. Fine. But it is true that when we are I can say making the partition walls as concrete walls, even it is a plain concrete wall, it will provide some resistance to the lateral resistance to the structure. Okay, or lateral stability to the structure. Okay, so if you see in high-rise structures, what they do, some of the walls where the concentration of the lateral forces will be higher, what they do, they provide some shear wall, and also they provide some RCC partition walls. Okay, so along with the shear wall, those RCC partition walls or RCC plain concrete walls also will provide some lateral stiffness to the structure, right? And rest of the wall they make by normal brick. Okay, that is also seen. So both are there, all the walls, concrete wall, the combination of shear wall and plain concrete wall. Some of the walls are shear walls, some of the walls are plain concrete walls, some of the walls are, you can say, brick walls. This is also seen. Okay, so the 𝗔𝗈 is just a formwork. You can have only your beam, column and slab casted with a 𝗔𝗈 formwork, and rest all the walls will be made up of brick, or you can say use the 𝗔𝗈 formwork for casting your plain concrete walls, shear walls also. Okay, so it's just a not our topic, but I have discussed, as many people ask, like how to design the 𝗔𝗈 walls. There is no wall called 𝗔𝗈 wall. 𝗔𝗈 wall just a formwork. The walls will be your RCC special shear wall or plain RCC concrete wall, plain concrete wall. Okay, plain RCC wall or plain concrete wall. Now design criteria will be as per IS 456 section 32 or as per IS 13920 section 10. Okay, so this is the design process, or you can say this is the design that you have to follow as per those sections. Okay, so I hope this is just an introductory session regarding the special shear walls. There are many criteria. If you see, if I open the IS 13920, see from here the clause started, then we have the ratios. Okay, aspect ratio, we have the minimum thickness criteria. If you see the minimum thickness criteria, we have you can say height to length ratios, we have the minimum reinforcement criteria. Okay, we have the stress criteria. Fine, we have the design shear also, for it should be designed for the shear forces also, so the shear design also provided. Then we have the boundary elements. Okay, so then we have again shear reinforcement for the boundary elements. So the whole section 10 covers the special shear wall. Okay, that we need to follow, and we will see later. Okay, so I hope you have got a bit idea about the special shear wall. Now I have not explained the things about the shear wall, like the shear wall is stronger in plane direction and weaker in the out of plane direction. So those are the things, those are the basics we all know. Okay, as the dimension of the shear wall is less in its out of plane, or suppose in this axis, and it is more in this axis, so obviously the stiffness of the shear wall will be higher here in this direction and will be less in this direction. So when the shear wall, suppose, so it is just an additional one I'm adding. So suppose we have a shear wall like this. I think I have one lecture regarding this, I have already uploaded, so that's why I was not explaining this. Suppose we have forces from this direction, we have forces from this direction. So when we have forces from this direction, suppose EQ, so then the shear wall will be deflected like this. And as so if you see, if I draw the, you can say, axis like this, so when the force is coming from this direction, we will have which bending moment? So we'll be having moment like this. Right hand thumb rule, will be having moment like this, right? Okay, and So it will be my mu plus mu. And when we are having forces from this direction, then the moment will be like this. But as per right hand thumb rule, it should be opposite. So it is minus mu. Okay, it is minus mu. So if you see, as the dimension in along this axis is higher, so we'll be having higher stiffness in this direction, and obviously we'll be having higher resistance of this force. But as the thickness compared to the other direction is very less in this direction, okay, sorry, very less in this direction, so due to this force or the resistance against this moment, the shear wall can resist this moment in a, you can say, very poor manner, because the stiffness is very less in the along this direction. Okay, so we will see this all these things, the design aspects, later. Mainly shear walls are designed for in-plane bending only, okay, or you can say to provide resistance along its longer direction, not in the shorter direction. Okay, so these things we will discuss later. So this session was about the introduction with the special shear walls. I hope it is clear to all of you. So again, if you have any doubt regarding this, you can write in the comment box. I will try to solve your doubts as early as possible. Thank you. And if you are not a subscriber of my channel, do subscribe the channel. I'll be you can say putting such you can say informatory videos on my channel, you can say quite often. And if you have any suggestion for me to, like, on which topics I should make videos, you can always write me in the comment box. I will try to cover those topics in my videos in future. Thank you, and see you in the next lecture.